It'll be good, baby. It'll all work out. Okay, good morning, lads and ladies. Thank you for showing up. I know that today being the day before Thanksgiving, it is might feel like it's asking a lot for you to be here. So I appreciate you being sufficiently responsible to do so. Today we're going to talk about a couple of things. I want to look a little bit more closely at parametric curves with you guys because you didn't get a proper lecture on Monday. And then I want to look at calculus operations with parametric curves, which we'll be doing two of. We'll be looking at, the textbook covers a few others, but we'll be looking at the tangents problem, if I'm finding a tangent line, or locating horizontal and vertical tangents for a parametric curve. And we'll also be looking at the arc length problem. So today, a bit more on parametric curves from 10.1 and calculus with parametric curves, which is 10.2. No class Friday. So the college is closed Thursday and Friday for the Thanksgiving holiday. So as much as it hurts to lose class this late in the semester, we will be losing a class on Friday. So I'll remind you what a parametric curve is. It's a curve coming from two equations. X is given as a function of time, and y is given as a function of time, independent of each other. And usually you'll have a time domain specified also. So the variable here is t. X and y are both dependent variables. T is the independent variable. So the thing you should think about is, you've got your t-axis over here, your domain. Maybe time is allowed to run from A to B like this. And you can kind of think of yourself as having a little slider. And then, as that slider moves, you have a point over here that sort of moves around. So maybe here's the point associated with time t equals A. This is the x-axis. This is the y-axis. There is no t-axis here. Your t-axis is totally separate out somewhere else. This point would be x of A, comma, y of A. We call that our initial point. And as you move this slider from A to here, you trace out this portion of the curve. And it has a direction because as t increases, the point moves from here to here. And then maybe it does all sorts of other crazy shit, who knows, until you get over here to t equals b, and the associated point x of b, comma, y of b. So really you should think of these as paths that particles, or maybe a little ant on the page, is walking along. He starts over here, and he marches all over the fucking place, wherever he wants, until you get to here. These curves can do a bunch of things that other curves cannot. First, you'll notice that this fails the horizontal line test. This fails the vertical line test. So x is not a function of y, and y is not a function of x. These curves can self-intersect. They can cross over themselves. They can do whatever the fuck they want. They are much more general looking curves than curves where y is f of x. The arrows indicate what we call orientation. These curves can be walked forward to backwards or backward to forwards. The point where you start over here is called the initial point. The point where you end over here is called the terminal point. I have an example queued up here in Desmos that I'd like to show you. Oh no, did I close? Oh no, I didn't. All right, here we go. Here it is. Right. So this is a parametrization of the unit circle. Here's the whole unit circle. This is x of t. This is y of t, and I'm plotting it as an ordered pair, x of t, comma, y of t. And t here is running from 0 to 2 pi. And then I've got a separate instance of that where you can watch me kind of move the point around. So you see your little ant walking along the unit circle?
It's not screen sharing.
Weird. Okay, I don't know why it's been doing that lately. It'll auto fix on the one I pick, right? So here's x of t. X of t here is cosine of t. Y of t is sine of t. And I've specified the time domain 0 to 2 pi. That'll give me the whole circle. And then I've just copied this down with a different variable so I can show you the point walking around. Really, I should let this run from 0 to 2 pi to give you the feeling. So there's my little ant walking around the unit circle, and I've got it set to repeat. Now I could change these functions. Another example that we've looked at was the cycloid. We talked a bit about this, and while normally I do go through the derivation of the cycloid, I've decided not to. It is a not great use of time, but t minus sine t. And then this would be 1 plus cos t. Oh, did I get something backwards here? 1 minus cos t, sorry. All right, and then if I copy this down here, s minus sine s, and 1 minus cos s. You see the same sort of thing, right? Now this path is famous for a few reasons. This curve is called the cycloid, and it's what you'd get if you started with a circle of radius 1 centered at the origin. Sorry, centered at the point, I gotta move this up, not centered at the origin. And you let it roll to the right. So if you imagine this point as starting at the bottom here, and you let this circle roll to the right, then as that circle rolls, if you track that point at the bottom, you will get this path. If you've ever seen a bicycle ride by and it's got reflectors on the outer part of the bike wheel, you see that cool kind of pattern that the reflector makes as the bike ride rolls by. That is a cycloid. That is this thing. The derivation of the equations here, x being t minus sine t and y being 1 minus cos t, it's a little bit complicated. It involves a lot of geometry, and it doesn't really help you understand what parametric curves are. So rather than go through that, I'd just like to show you 1 or 2 more examples here. Let me grab something kind of interesting looking. Let's look at this, e to the negative t plus t, e to the t minus t. So my x function here is e to the negative t plus t, and my y function here is e to the e to the t minus t. Something like this, e to the negative t plus t, and we'll go, they wanted to go from -2, we'll go -10 to 10 or something. And then I'll just copy this down. Negative s, comma, plus s, s plus s. And this piece would be e to the s minus s. Okay. So again, here you should see a particle moving along this path. Oh, e to the negative s. There it is. See a particle moving along this path as the variable runs over those values. Pretty cool stuff, right? So this particle is moving along this curve. The curve is the parametric curve, and it is the path that is traced by this particle's motion. What I want to talk about today is how to find the tangent line anywhere along this curve. And the trick to finding the tangent line is really the chain rule. So I'm going to come back to the doccam now. We want to say, you give me some point along this curve. Can I find the equation of the tangent line at any point along this curve? Can I find the points where the tangent line is horizontal or where the tangent line is vertical? All of the Calc 1 questions that you asked about curves that come from functions, can you answer those same questions here? Of course, the answer is yes. So we're going to begin with finding tangents. Now, no, baby. I cannot be doing that shit here. So, recall the Leibniz notation for the chain rule. If you know, let's see, if y, that's not how to say this. If y is a function of x and x is a function of t, then by the chain rule, dy dt would be dy dx times dx dt. Now, it's not true that everywhere here y is a function of x, right? At all the places where this thing fails the vertical line test, I cannot say y is a function of x. But using what's called the implicit function theorem, I can say that anywhere, as long as I stay away from these vertical tangent spots, I can think of y in every little window here as being a function of x, and that makes this calculation valid, which would mean if you divide both sides by dx dt, you get that dy over dx is dy dt divided by dx dt. So this is our first kind of important formula. That'll let you get the old-fashioned derivative, dy dx, which is the slope of the tangent line, in terms of the time derivatives, the derivatives of the y function and derivatives of the x function. So you take the derivative of the y equation, take the derivative of the x equation, divide them, and that will give you dy dx, which is the slope of your tangent line. The catch is, the thing you need to remember, this will be in terms of the variable t. So the variable here is not going to be x, it's not going to be y, it's going to be t, which means all of the work that you would normally do with the derivative, you can still do it. You just need to be mindful that that the variable you're playing with is neither x nor y. So if you want to know like a point where you have a horizontal tangent line or something like that, you would do the normal work here, setting the derivative equal to 0. But then that would give you out a t value, not an x value. So you would need to then plug that t value back into the two original equations, x and y. Plug the t value in here, plug the t value in here to get the point. Or conversely, if you're trying to find the tangent line at a point, you first need to find the t value associated with that point. Then plug that t value in here in order to find your slope. So the best way to get comfy with this stuff is just to play with it. I'll give you a second in case you're writing down any of these things, and then we're going to move on and actually do a calculation or two. Okay, let's do a calculation. I'm going to take this from your textbook. There's a few good examples in here that I do like. All right, so here's the result we just cooked up. Let's take this guy. Yeah, y. So x is t squared, y is t cubed minus 3t. And let's find any points, x comma y, where the tangent line is horizontal. Now, just for fun, I'm going to plop this into Desmos. T squared, t cubed minus 3t. We can take a look at it. Pause this. So my x function here is just t squared. My y function here is t cubed minus 3t. I'll copy that down here just so we can watch the particle move. T squared, or sorry, s squared, right? And then s cubed minus 3s. So here's what that curve looks like. And you can see that there definitely are, there is a point up here where the tangent line is horizontal, and there's a point down here where the tangent line is horizontal. And if I let my slider move, you can see the point running along here. So looks like the value of the parameter, where I'll have one of these horizontal tangents is -1, and the other value will be down here at like maybe +1. Let's see if that agrees with what we find here. So a horizontal tangent line, HTL, this is the same thing as saying dy dx, the derivative, is equal to 0. And I can calculate dy dx as dy dt over dx dt. dy dt is what you get when you take your y equation and you differentiate with respect to time. So that's going to be 3t squared minus 3. And if I differentiate this x equation with respect to t to get dx dt, that's just 2t. You can factor a 3 out from the top, and that becomes t squared minus 1, so that's t minus 1 times t plus 1 over 2t. So dy dx is equal to 0. When is this apparatus equal to 0?
One and -1.
Yeah. Which is what we found, right? Which is what we were suspecting from looking at this picture, right? Up here at 1, -1, and 1. We have these two spots where we look like we have horizontal tangents. Now, I didn't want t-values. Here's the catch, right? They said find any points x comma y where the tangent line is horizontal. And all I have are values of t. So to find the points, you need to plug these t-values in. X of 1 comma y of 1, which is 1 comma, what's y of 1? If I plug 1 in here, that's 1 cubed minus 3 times 1. That's 1 minus 3 is -2. And x, oh shit, x of, I'll do it down here. And x of -1 comma y of -1. If I plug -1 in for x here, this is still -1 squared, which is 1. And if I plug -1 in here, that's -1 minus 3 times -1. That's -1 plus 3 is +2. So indeed, the 2 points with horizontal tangent lines are the points we suspected. These guys. All right. The other thing we like to look for are vertical tangent lines. And at a glance here, I see that I have a vertical tangent line at the point 0, 0. But how would I find that? So if you're looking for stuff to save, in addition to that formula for dy dx, remember horizontal tangent lines happen where dy dx is equal to 0. So you need to take your dy dx in terms of dy dt and dx dt. You might need to simplify this a little bit and then set it equal to 0. Now, solving equations like this thing equals 0 is something that you learned how to do back in pre-calculus. There's a whole section there on rational equations and rational inequalities. If you've forgotten any of that stuff, you may want to go back and refresh it a little bit. And if you happen to find a t-value that made both the top and the bottom 0, then you would need to use L'Hopital's rule to look at that more carefully as a limit to see whether dy dx is actually 0 at that t-value or something else. But basically, to solve an equation like this, you'll set the top equal to 0. If the top is 0 and the bottom is not 0, then this whole thing is equal to 0. If the top and bottom are both 0 at the same t-value, say t equals 5, makes both the top and bottom 0, then you would need to take the limit of this as t approaches 5 and use L'Hopital's rule to figure out whether that is really a solution to dy dx equals 0 or not. Vertical tangents, on the other hand, maybe I call this part A. And part B, I want to find any points x comma y where the tangent line is vertical. And vertical tangent lines correspond to what happening with the derivative? What's the slope of a vertical line?
Undefined.
It is undefined. It's a particular kind of undefined, though. It means that dy dx, the slope of my tangent line, has to be tending towards plus or minus infinity. So I'll show you an example from the Calc 1 sense, and then we'll return to our guy here. The classic Calc 1 example of a vertical tangent line. Clear all this out. Classic Calc 1 example of vertical tangent line is something like y equals x raised to the 2/3. And you see here at 0, this tangent line is becoming more vertical. So I'll call this, in fact, f of x. I could say y minus f of a equals f prime a times x minus a. We can have a slider for a. And here's your tangent line, right? And you notice that as you get closer and closer to 0, I'm going to take smaller steps. As I get closer and closer to 0, this tangent line gets more and more and more and more vertical. So what does that mean? That means that the derivative, which is f primed, is blowing up to infinity. And you see that here, right? Here's the graph of the derivative. As x gets closer and closer to 0, the graph of this derivative is blowing up to positive infinity on one side and negative infinity on the other side. So to find vertical tangents for f, you figure out where f primed is blowing up to infinity or negative infinity. The square root function also has a derivative which is undefined at 0, but he doesn't have a vertical tangent there because his derivative, while his derivative is undefined at 0, it's not blowing up to infinity. So I just want to make that little distinction. So we need to discover where dy dx is going to infinity. And here, that's not anything hard because dy dx is still 3 times t minus 1 times t plus 1 over 2t. This apparatus goes to infinity as the bottom goes to 0, right? If you take something that is non-zero and you divide it by something that is very, very close to 0, then you'll get something that is very, very close to infinity. So this goes to plus minus infinity as t goes to 0. In other words, I have a VTL dy dx goes to plus minus infinity as t goes to 0. So my point is x of 0, comma, y of 0. And x of 0 is what you get by plugging 0 into the x equation. The x equation, x of t is just t squared. So x of 0 is 0. And y of 0, if you plug t equals 0 into the y equation, you get 0 cubed minus 3 times 0. That's also 0. So just as we suspected, the vertical tangent line is at the origin, and the two horizontal tangents are at 1, negative 2 and 1, positive 2. I'd like to show you one other problem with this curve, but first, any questions on finding horizontal or vertical tangents for parametric equations, parametric curves? Okay. So one more problem with this guy. Let's find the equation of all tangent lines at the point, is it 3, 0, I think? Yeah. Now, the interesting thing about the curve we're playing with here is that it goes through that point more than once. Here's the point 3, 0. We go through that point once on the way up here as my point comes in, and then once again on the way out. So there's really two tangent lines here because this curve self-intersects. So before I can get started finding my slope and plugging into my point slope formula, I need to find the two t values associated with that point. And anytime you're asked to find the tangent to a parametric curve at a specific point, you need to begin by finding the t value. In this case, there's more than one, so we're going to find the t values at the point 3, 0. Any ideas how we could do that? How do I find out what t value makes my curve be at that point 3, 0?
Plug in the 3 for x of t and the 0 for y of t, and then solve as a function of t.
Yeah, good, good. So I know x is equal to 3 at that point, and y is equal to 0. So I need to solve the two equations, x of t equals 3, and y of t equals 0. And I need t values that make both of these things true at the same time. So t squared is equal to 3, and t cubed minus 3t is equal to 0. Here you can take square roots and you get t is plus and minus the square root of 3. So the x coordinate will be 3 at the two times t equals plus root 3 and t equals minus root 3. But maybe not both of these have the y value being 0. So we should check this also. If I factor a t here, I get t times t squared minus 3 equals 0. So here I get either t equals 0 or t squared equals 3, which would be t equals plus minus the square root of 3. So two of these match. This guy does not match. T equals 0 does not make my x coordinate equal to 3. So he's not one of the guys I'm interested in. The two guys I'm interested in are, so our curve goes through 3, 0 at 2 times t equals negative root 3 and t equals positive root 3. At time t equals 0, we're going through the point 0, 0, not 3, 0. So these are my two times. Maybe I'll call this T1 and call this T2. So I'm going to find two tangent lines. I'm going to find the tangent line associated with T1 and the tangent line associated with T2. All right, I've got some space here, so I'll do my derivative calculation there. dy dt is still 3t squared minus 3. dx dt is still 2t. So dy dx is still 3t squared minus 3 over 2t. So my first slope I'll call it M1 is dy dx evaluated at t equals t1, which is negative square root 3. So the slope comes from the derivative like always. The catch is you're plugging in t values now, not x values. That's all you got to remember. Other than that, it's just like Calc 1. So this is 3 times negative root 3 squared. I factored the 3 there. That's okay. So I'll write it as this minus 3. It's a little redundant, over 2 times negative root 3. Negative root 3 squared is 3. So this is 3 times 3 minus 3 over negative 2 square roots of 3. That's 9 minus 3, that's 6 over negative 2 square root of 3. You can cancel the 6 and the 2, so that's negative 3 over the square root of 3. But nobody would write it like that. If you rationalize the denominator here, then you'll just find that this is equal to negative square root of 3. So that's your first slope. And the point is still the same point, is 3, 0. So by the point slope, the point slope equation for a line, our tangent, our first tangent, is y minus 0 equals this slope times x minus 3, or just y equals negative root 3x plus 3 root 3. And you can check, you can put this in Desmos. There it is. There's your tangent. So this is the tangent line that we get on the way in. Right, this tangent line is the tangent that represents the particle at the moment it's coming in, and remember it loops around and then goes out. So the other tangent line is going to be over here. And we'll get that by doing a very similar calculation, just instead of plugging in negative root 3 to the derivative, I'll plug in positive root 3, my other time. So here's our first tangent line. The second tangent slope, just the second tangent, I'll say slope, we said slope in the first time because that's what we're really starting to calculate here, is m2 equals dy dx evaluated at the time t equals positive root 3, which is 3 times root 3 squared minus 3 over 2 times root 3, which the top is still 3 times 3 minus 3 is 6. The bottom here is 2 root 3. And again, you can cancel the 2 into the 6. You get 3 over root 3. And again, you can rationalize the denominator, and here you just get slope is positive square root of 3. So again, using point slope, remember the point of tangency is the same in all of these. It's 3, 0. So this will be y minus 0 equals square root 3 times x minus 3, or just y equals root 3x minus 3 root 3. And if I were to graph this guy as well, you'll see both of those tangents in root 3x minus 3 root 3. All right, so there's both of those tangent lines. So this curve, because it self-intersects at the point 3, 0, there's multiple tangent lines. Each one of those tangent lines comes from plugging the appropriate time into the derivative. Beyond that, it's just like it is in Calc 1. You just use the point slope formula, you come up with your slope using the derivative, and then you plug in the point slope. Nothing crazy. Questions on this? Questions on tangent lines to parametric curves in general? Okay, then I'm going to move on to talking about arc length. The other calculus operation that I care a lot about in the setting of parametric curves is arc length. You can solve the area problem here, sure, but it's boring. You can't do anything with areas that in parametric setting that you can't do in the regular setting. There's nothing really new learned here. But I think thinking about arc length in terms of parametric curves is not only nice, it's the right way to think about it. So that's what we're going to do now. We're going to talk about arc length of parametric curves. And as always, I'm going to think of myself as having a little t-axis somewhere out, totally removed. And I'm interested in the t interval from A to B. And then here is my xy axis, completely separate from the t-axis. And I'll draw in just a little kind of arbitrary parametric curve. Maybe it starts over here and does something like this, ends over here. So this point would be x of a comma y of a. This point over here, the terminal point, x of b comma y of b. And remember what we did when we were solving the arc length problem in the function setting. We chopped up our domain, which there was an interval of x values, into a bunch of equal length pieces. And then we looked at the corresponding points, and then we approximated the length on each of those subintervals by straight lines. I'm going to do the same thing here. I'm going to call A T0, and then I'm going to chop this up into a bunch of little subintervals. So this would be T1, T2, T3. I'll call this Ti minus 1 and Ti. And then the last guy here, B, would be Tn. So we chop the time interval AB into n equal length pieces, each of length, call it delta t, and that's b minus a over n. And then associated with each of these t values, t1, t2, t3, is a point. I'll call them p1, p2, p3. On and on and on. Maybe over here is Pi minus 1, and over here is maybe Pi, and so on. You know, this would be Pn. And I'm going to approximate the total length by looking at all these straight line lengths. You know, there would be a bunch more in here. as n goes to infinity, the blue is going to stick closer and closer and closer to the purple. So the length of each of these, I'm going to take the pi minus 1 to pi to be my sort of arbitrary guy. The length from pi minus 1 to pi, I can think of in terms of a little right triangle, just like we did before. The catch is that these are not equally spaced, right? Like you notice the length along the curve from here to here is way different than this. And the x values, the x distances are not always the same. The y distances are not always the same. So here I'll call this delta yi, and here I'll call this delta xi, with the knowledge that both delta yi and delta xi change from point to point. Neither one is constant. Then by Pythagoras, the distance here is the hypotenuse of this right triangle. Maybe I can come in with some more color. Purple. Right, if you look at this little right triangle, then you see this squared has to be this squared plus this squared. So the distance from pi minus 1 to pi squared is equal to delta yi squared plus delta xi squared, which means that the distance from pi minus 1 to pi, the distance between any two consecutive points, is the square root of delta yi squared plus delta xi squared. I'm going to switch back to purple now. So my total length, S, is approximately the sum of these little lengths, the sum from I equals 1 to n, length from pi minus 1 to pi. That is exactly the sum from I equals 1 to n, square root of delta yi squared plus delta xi squared. And now I'm going to do something very sneaky, like we did before. I'm going to multiply by delta t over delta t. Nobody can stop me from doing that. I'm just multiplying by 1. Delta t is a positive finite quantity. I can multiply and divide by it. It's not 0. It's not infinity. And then the one from the bottom, I'm going to treat like the square root of delta t squared. So my next step is to say this is the sum from I equals 1 to n of the square root of delta yi squared plus delta xi squared times 1 over delta t squared. And then the other delta t over 1, I leave him outside the square root. So this guy from the bottom, he's going to go inside the square root as delta t squared. So he's a factor. I can shove him in or out. If he's under the square root, then he needs to be squared. If he's out of the square root, he's on his own, right? If you take the square root of this thing, you do get this, because delta t is positive. You can do that. And now I'll just distribute this. So it's just a little bit of sneaky algebra. And what I get is delta yi over delta x. And each of those, or sorry, delta Don't write that down. Slip of the pen. What I get is sum I from 1 to n square root this divided by this plus this divided by this. So that's delta yi over delta t all squared plus delta xi over delta t squared. And then outside the square is still this delta t over 1. I'm just going to leave that as delta t. Okay. And this again is looking like a Riemann sum. As n goes to infinity, this will become dy dt, and this will become dx dt, this will become dt, and this will become the integral from a to b. So as n goes to infinity, two things happen. The first is that delta y over delta t becomes dy dt. Delta x over delta t becomes dx dt. And delta t on its own becomes dt. The second thing that happens, I just can't get my notation right today. Second thing that happens is that the approximation becomes exact. So we get the exact arc length is equal to, I should say, and capital sigma here becomes an integral, right? So the exact arc length is the integral from t equals a to t equals b. They're times, remember that, the square root of dy dt squared plus dx dt squared, all done dt. So this Riemann sum turns into this integral, and the approximation becomes exact. You're using infinitely many, infinitely short little lines. So you get the exact arc length. To me, this is way more satisfying than the arc length formula in section 8.1, even though they're doing the same thing. And your book, rather than deriving this independently like I did, they cook this up as a consequence of the formula in 8.1, which I don't like. To me, this looks more like a Pythagorean thing. This looks like a bunch of teeny tiny little hypotenuses, which is really how we're thinking of that curve. The book does have a picture, which is okay. Probably a little better than my picture. Well, it's about the same as my picture. And to me, this just looks more Pythagorean. This looks nicer than the formula you had back in chapter 8. Now, they do get this formula from this formula. It can be done. It's not hard. But I think it's way more fun to cook it up raw like we did. But what you guys need to worry about is being able to use it. So here's the formula. This is the length of the parametric curve. So let's get some practice. Let's find the exact length of one arch of the cycloid x of t equals, I can never remember this, y of t equals, do it here. I think they have this somewhere in here. Yeah, 1 minus, oh wait, no. T minus sine t, 1 minus cos t. All right, so the picture is this. Again, I'll remind you what the picture of that cycloid looks like. Yeah, and it continues on and on like this forever. They kind of look like halves of ellipses, but they're not. They're their own shape. They're not halves of ellipses. And we're trying to find the length of just one arc. So that's from here to here. So before I get started, I need to know, what are the t values there? And then I'll need to take these derivatives and plug everything into this formula. The easiest way to find these t values, these are the first two positive solutions to y of t equals 0. So I need to find the first two positive t values which make y of t equal to 0. So I need to solve 1 minus cos t equals 0. And that has infinitely many solutions, but I just need the first two positive solutions. So that's the same as saying cos t equals 1. What are the first two positive solutions to cos t equals 1? Where is cosine equal to 1?
Pi and
I should say non-negative. Now the cosine of pi is -1, but 0 and 2 pi. Yeah, I shouldn't say positive. I should say non-negative. So these are t equals 0 and 2 pi. Of course, there's infinitely many solutions. 4 pi, 4 pi, 6 pi, 8 pi. Also, -2 pi, -4 pi, -6 pi. Any even multiple of pi will work. So this one is 0. This one is 2 pi. The next one here would be 4 pi, and so on. Then the pieces that I need to build my arc length integral are dy dt, the derivative of the y function taken with respect to time is 0 minus cosine t, the derivative of cosine t, which is negative sine t, so this is just positive sine t, and dx dt, the derivative of the x function here is just 1 minus cos t. So my arc length S is the integral from 0 to 2 pi square root of dy dt squared, which is sine t all squared, plus dx dt squared, which is 1 minus cos t all squared dt. So my task is now to evaluate this integral. Questions on how we got here? Okay. So I'm going to just simplify under that radical and see what I can do. This is the integral from 0 to 2 pi square root of sine squared t plus 1 minus 2 cos t plus cos squared t, just foiling things out. And that's all under this radical. I can combine the sine squared and the cos squared. This is sine squared t plus cos squared t plus 1 minus 2 cos t, all under this radical. And sine squared plus cos squared is 1. So I've got 1 here, plus 1 there is 2 minus 2 cos t. Anyone got a clue how the fuck I integrate that? It's not something we've seen before. Do we remember this identity? Half angle identity for sine. If I multiply through this by 4, four times 1/2 is 2. So 4 sine squared theta is 2 minus 2 cos 2 theta. So I've got a 2 minus 2 cosine. This is the sort of thing I want, right? This is looking a lot like what I have here. And conveniently, the thing on the left-hand side here is a perfect square, which is nice because I want to take the square root of this. So now if we replace theta equals t over 2, this is a theta. This becomes 4 sine squared of t over 2 equals 2 minus 2 cosine of 2t over 2, which is t. So this piece is equal to this. It's clever work with the trig identity. We get integral 0 to 2 pi 4 sine squared t over 2 under my radical dp. There's other ways to get at this, but this is, I think, the best way. It just works from a trig identity that you know, a trig identity that you had to use a lot at the beginning of the term. If you wanted to, you could force factor a 4 here and make this show up exactly. But you still need the theta equals t over 2 thing. So it's a little bit tricky. That's why I wanted to walk through this with you. And now we can take the square root of this. The square root of 4 is 2. The 2 can come out. I'm going to come over here. So I get 2 integral 0 to 2 pi. The square root of sine squared t over 2 is the absolute value of the sine of t over 2. Remember, when you take the square root of x squared, you don't just get x, you get the absolute value of x. So I need to see if this function is positive from 0 to 2 pi? If it is, then I can ditch the absolute values. If not, then I'll have to split it up. I'm going to mark this as 4 pi. You should remember that the period of this function is 2 pi divided by whatever the number is inside. The number inside here is 1/2. So the period here is 4 pi, which means a half period is 2 pi, a quarter period is pi, and 3/4 period is 3 pi. So the graph of this function, graph of sine t over 2, where this is the t-axis, this is the y-axis, looks like this. In particular, from 0 to 2 pi, this thing is positive. So I can lose the absolute values. This is just 2 integral 0 to 2 pi sine of t over 2 dt, and you make a little substitution, u equals t over 2, du is 1/2 dt. Your bounds will change. When t is equal to 0, u is 0 over 2, so that stays 0. When t is equal to 2 pi, u is equal to 2 pi over 2, that's just pi. So there's our substitution. And this will be 2 times the integral from 0 to pi sine of u times, I solve this for dt, and I get 2 du. So we'll have 4 integral 0 to pi sine of u du, which is 4 times negative cos of u, evaluated from 0 to pi, which is 4 times negative cos of pi minus negative cos of 0, which is 4 times negative 1 plus 1, which is 4 times 2 is 8. So the length of one arc of the cycloid coming from a rotating wheel of radius 1 is 8. It's a nice number. It's kind of cool. So if your bike wheel had radius 1 meter, say that would be an enormous bike wheel, but 1 foot would be too small, then as you roll and you track one point's motion along the top of that bike as that bike wheel goes around, it would go 8 meters. Pretty neat stuff, right? I know this integral was a little bit tricky with that trig identity, so I want to give you a second to sort of digest and ask any questions. Thoughts, concerns, questions?
I kind of missed what the whole absolute value thing was.
So remember that the absolute value of, let me say it this way. If you take the square root of x squared, what do you get? Most of us just want to call this x, right? Saying the square and the square cancel out. But that's not correct. What you actually get is the absolute value of x, because feed this, if x is -1, then the square root of -1 squared is the square root of 1, which is 1. Or if x is -2, then the square root of -2 squared is the square root of 4, which is 2. So you see, I'm not getting x, I'm getting the absolute value of x. Now, if you want to integral from a to b, absolute value of some function. So this is why the square root of 4 sine squared t over 2 is the absolute value, 2 times absolute value of sine t over 2. The square root of 4 is 2, and the square root of sine squared is the absolute value of sine. And then something you may or may not remember from Calc 1, if you want to integrate the absolute value of a function, maybe a is here, and maybe b is over here. These pieces are already positive, but I would have to break it up to make this piece positive as well. So the way you would do this integral is integral a to c f of x dx, and then minus, to correct for the fact that this is negative, integral c to d f of x dx, and then plus integral d to b f of x dx. In other words, if you're integrating the absolute value of a function, you need to figure out where that function is positive and where that function is negative. Where that function is positive, like from a to c and d to b, you can just integrate that function because the function is the same as its absolute value. But where that function is negative, you need to slap another negative on to correct and make it positive. So this is the graph y equals f of x. The graph y equals absolute value f of x, the thing you're actually trying to integrate, would look very similar. But here, this piece would be flipped up. All right. So to flip this piece up, you need to negate it. It's already negative. To make it positive, you need to negate it again. In this case, it's not consequential because the sine of t over 2 is positive everywhere from 0 to 2 pi. I'm just looking at this region. So the absolute value of that thing is just that thing. That's all this step was about. So here I'm taking the square root carefully. The square root of some stuff is not, the square root of some stuff squared is not just that stuff, it's the absolute value of that stuff. And if this happened to be negative sometimes, if the sine of t over 2 was negative anywhere between 0 and 2 pi, I would have to split this integral up like you did in Calc 1 in Chapter 5, 5.3. But here, since the sine of t over 2 is positive everywhere between 0 and 2 pi, I didn't need to worry about it. I could have just jumped to this and been fine. If this sounds strange, if you don't remember this sort of stuff, then I would advise taking a look. It's a section that a lot of Calc 1 teachers don't cover well enough. Definite integrals, absolute values. We'll get it here somewhere. I think mostly they talk about it when they talk about the net change theorem, actually. Is this it? No. Getting there here, right? So when you want to integrate an absolute value function, you need to be very careful to make sure that you're correcting for places where the function is negative. I want to measure this area as positive, even though it's beneath the x-axis, or here beneath the t-axis. So what you want to do is add these areas, a1 plus a2 plus a3. But a2 here would be negative as an integral. If you integrated, this area would be counted as negative. That's what they're saying here. How do you fix that? Well, the way to fix it is to split up the integral like they do here. Because we're negative from 1 to 3, and we're positive from 3 to 4, if you want to integrate the absolute value of that function, you need to negate it where it's negative to make it positive, and then you leave it alone anywhere it's positive. Another way to do this, we can say, Oh, look, they've even got absolute value of trig functions. So you can take a look at some of these videos. They would be helpful. Let me see if I can find one that I trust. Yeah, tell you what, let me do this. Let me do this after class. I can find something there, and if you want to see it, send me an email or a Canvas message, and I'll hit you up. In practice, the problems I give you, I will avoid this issue. It's just an issue I wanted you to be aware of. That when you take the square root of something squared, you don't get that thing, you get the absolute value of that thing, and so you need to treat it with the care that you would back in Calc 1. In practice, in the arc length integrals I'll give you, you won't need to stress about it. I'll design the problem so that's not the case, but it is something you should be aware of. So if you want to see those details, let me know. And if you like, I'll look them up and send them to you in a Canvas message or post an announcement if more than one people wants to see them. Other questions on this? On arc lengths or tangents in general for parametric curves? Any other questions at all before I let you go? All right, then this is where I will leave it for today. Go ahead and try to knock out the homework. I'm sorry I didn't get the homework on Monday. I just forgot to publish it for you guys, but I did publish it yesterday morning. So go ahead and get grinding on that. It's not terribly hard. I think everything you'll find is fairly straightforward. Some of the arc length integrals can be a little bit tricky. If you get stuck on any of them, please don't hesitate to reach out to me. I'll have my normal office hour this afternoon, but no office hours tomorrow or Friday due to the Thanksgiving holiday. I know that Thanksgiving is a time to be lazy, but please don't be all the way lazy. Remember to spend at least a little bit of time each of those 2 days and over the weekend, of course, doing mathematics. You do have an exam coming up. Exam 3 is next Friday. Next Friday is our last day of class, December 4th, and that is when exam 3 will take place. So this Friday, I will be publishing the study guide for that test. If I get it done sooner than that, I'll go ahead and put it out sooner, but I have exams from another class I need to start grading. So probably this Friday, you can see the study guide. And that is it. We'll have regular class next Monday and Wednesday, and the next Friday is your exam 3. And then the final will be the following week. I believe you guys have your final. Let's see, this is section 2. Your final will be December 9th at 8 a.m. So I'll post some announcements reminding you about the final and make sure you hand in the exam 3 study guide on the day of exam 3. And that is it. All right.
Is
Yeah.
this the last material for exam 3?
So next week we're going to cover polar coordinates, and I will, unfortunately, it's just the way the class works. At the end here, we don't get to have a week break between the last material for exam 3 and exam 3 itself. So next Monday and Wednesday, I'll be teaching you guys how to solve these problems in polar coordinates, and then on Friday, you will be tested on that. I know that that sucks. I know that that sucks. So what I'm going to do is the polar coordinate material on exam 3 is going to be very gentle. And then I'll put a little bit more polar coordinate stuff on the final. So basically exam 3, the exam next Friday, is going to emphasize power series, arc length and surface area from chapter 8. And then it will have a little bit of parametric curve stuff and a tiny little bit of polar stuff that we'll learn about next Monday and Wednesday. But the vast majority of the parametric and polar stuff that you'll be tested on will be done on the final. So when studying for exam 3, focus on the power series material and on the chapter 8 material. And then the chapter 10 material, while it will be present on exam 3, it will be very, very gentle. And the rest of the chapter 10 stuff you'll see represented more on the final. Does that make sense?
Okay, thanks.
All right, cool. Alrighty then, I will see you guys either in office hours or next Monday. I hope you have a lovely, safe holiday. Please take care of yourselves. And don't forget to do some math.